In the previous video, we introduced mixtures, a broad category of substances which include solutions, colloids, and suspensions. Today, we're going to build on that knowledge as we talk about molarity. Let's start with a quick review of last time. We now know that a solution is a type of homogeneous mixture in which the dissolved particles are too small to see or be physically separated. All solutions are composed of a solvent and one or more solutes, where the solvent is the substance doing the dissolving, and the solute or solutes are the substance or substances being dissolved. The concept we're going to focus on today is concentration. The word concentration has quite a few definitions, obviously, but in chemistry, concentration is the ratio of the amount of solute to the unit amount of solution. In other words, how much solute can be found in an amount of solution. That's what concentration helps us measure, and it is specific to solutions. Now, the amount of solute in this ratio can be expressed as either a mass amount or in moles. When we express concentration as a mass amount of solute in a unit volume of solution, we call it the mass concentration. The SI unit for mass concentration is the kilogram per cubic meter, which is equal to the gram per liter. At the end of the day, however, we can really use any unit of mass over volume to express mass concentration. Some viewers might notice that these units are the same units used to express density, and in a way, we can view mass concentration as basically the density of a solution, if it helps to think about it like that. On the other hand, we have molar concentration. Molar concentration is the moles of a solute dissolved in a unit amount of solution. The term molarity is a synonym for molar concentration. The SI unit for this parameter is the mole per liter, which is often abbreviated simply as the capital letter M, as shown here. This means that when we say unit amount of solution, we usually mean in 1 liter of solution. However, it's also possible and acceptable to express molarity using other units of moles per liquid volume, such as the kilomole per liter and others in that vein. From a conceptual point of view, a higher mass or molar concentration means that more solute is dissolved in the solvent, and this means that the solution itself is more concentrated. Here's what we mean. Down here, we have two solutions. The one on the left has a molarity of 1m, and the one on the right has a molarity of 5m. Both solutions are sodium chloride, or NaCl, dissolved in water. So sodium chloride is our solute, and water is our solvent. Each of these blue dots in the solutions represents a particle of sodium chloride. Because both solutions are comprised of exactly 1 liter of water, the 5m solution ends up having far more salt particles in it, and if you were to take a sip from both these solutions, which I do not recommend doing, we would find that the 5m solution has a much stronger salty taste than the 1m solution, because of how many more molecules of sodium chloride are dissolved in the former. It's time for our first example problem of the day. Example 1 says, 17 grams of sodium bromide are dissolved in 100 milliliters of water. Calculate the molarity. Feel free to pause the video if you'd like to try this for yourself. This problem isn't necessarily difficult on its own, but we need to be careful not to fall into any traps here. The problem gives us the values in terms of grams and milliliters, so we'll need to convert these values. The molar mass of sodium bromide is 102.89 grams per mole, so we divide 17 grams by 102.89 to obtain 0.165 moles of sodium bromide. 100 milliliters is equal to 0.1 liters, so all that's left to do is to divide 0.165 by 0.1. Our final answer is 1.65 moles per liter, or 1.65 m. One practical application of molarity becomes obvious when we apply it to stoichiometry. We call this solution stoichiometry, and it's important to know how to do this. The best way to illustrate this concept without going into a long and unnecessary review of stoichiometry is to do a problem. Example 2 says, how much 0.5 m potassium nitrate must be added to a solution of 2 liters of sulfuric acid concentrated to 3 m if all the potassium nitrate needs to react? What we have going on here is the mixing of two solutions. On the one hand, we have a 0.5 m potassium nitrate solution, and on the other hand, we have a 3 m sulfuric acid solution. We can write a chemical formula for this, but since we aren't given any other information, let's assume that the molar ratio between potassium nitrate and sulfuric acid is 1:1. Our next step is to write down the volume of sulfuric acid. 2 liters. Now we convert this into moles. We don't use the molar mass in this instance. Instead, we use the molarity, which is 3 moles over 1 liter. And once again, we're assuming the molar ratio is 1/1. Our final step is to multiply all this by the inverse of the molar concentration of potassium nitrate, which would be 1 liter over 0.5 moles of potassium nitrate. If we multiply across and cancel all the required units, we will get an answer of 3 liters of potassium nitrate. Before we move on, I did want to expound a little more on solution stoichiometry problems specifically. Generally speaking, there are 2 main applications of solution stoichiometry. The first are problems similar to the one we just did, problems which involve an acid. Such problems will usually ask something along the lines of, how much of substance A at a molar concentration of blank are needed to neutralize a solution of acid B at a molar concentration of blank. The second type of problem encompasses those which will mention a precipitate. We'll talk more about precipitates later in this unit, so don't worry too much about that right now. But these are the situations in which we are likely to encounter solution stoichiometry. We might be wondering how the molarity of a solution might change. It is in fact possible to both increase and decrease a solution's molarity. To increase the molarity, we can either add more solute or remove some of the solvent. Both actions will increase the concentration of solute molecules in the solution and thereby increase its molarity. To decrease molarity, our only option is to add more solvent. Again, a solution is a homogeneous mixture whose solute particles cannot be separated through physical means like filtration, so it isn't really possible to remove the solute in most cases. Now, when it comes to increasing and decreasing molarity, we can assign special names to both these processes. Increasing molarity is confusingly referred to as concentration, or concentrating a solution, whereas decreasing molarity is called dilution, or diluting a solution. This right here is the major formula when it comes to calculating concentrations or dilutions. M1 times V1 equals M2 times V2. M1 represents the initial molarity, V1 represents the initial volume of the solution, and M2 and V2 represent the final molarity and final volume of the solution, respectively. Let's put this formula to use. Example 3 says, consider the following solution of copper sulfate in water. This solution is 100 milliliters in volume and has a molarity of 2m. How much water must be added to dilute this to 0.6 m? This should be easy enough. All we need to do is apply the formula. Initial molarity is 2m. Initial volume is 0.1 liters. Be sure to convert the volume into liters if it isn't already. It isn't strictly necessary to solve the problem itself, but molarity is moles per liter, so it makes sense to work in liters. So we have 2m multiplied by 0.1 liters is equal to 0.6m times our unknown variable, or V2. We solve for V2 to get our answer. .33 liters, which is equal to 330 milliliters. But this is not our final answer. If we read the question up here, we'll see that it's asking how much water must be added to accomplish this dilution. What we have here is actually the total volume of the final solution. To obtain the answer for how much must be added, we need to subtract the initial volume from the final volume. And 330 minus 100 is equal to 230 milliliters, or 0.23 liters. Here's another one. Example 4 states, a nurse is preparing medicine for IV or intravenous administration. The patient needs a dose of medicine at 1.2 m, but the 100 milliliter dose at the hospital is concentrated to 0.5 m. How much powdered medication should the nurse add to the existing supply? Assume the medication's molar mass is 148 grams per mole. So this problem wants us to find out how much additional solute is needed to concentrate an existing solution. Pure logic tells us that we can't modify the volume of the solution, so the final volume V2 is going to be equal to the initial volume V1. To determine the amount of solute required, we have to combine our knowledge of stoichiometry and solutions once again. We know that the final solution must have a molarity of 1.2 m, which is equal to 1.2 moles of medication in 1 liter of solvent. but the dose is only 120 milliliters, or 0.12 liters. To find out how many moles of solute must be in this dose following our concentration, we set up a ratio. 1.2 moles over 1 liter is equal to x moles over 0.12 liters. We cross-multiply and solve for x. We find that we need 0.144 moles of solute medication for an effective 120 milliliter dose. We can then convert this to grams using the provided molar mass. 0.144 times 148 grams per mole equals 21.312 grams. But don't forget, this is the final amount of solute, not the amount the nurse needs to add. Again, we have to find the initial amount. We use our ratio method again. Initial molarity is 0.5 moles over 1 liter equals y moles over 0.12 liters. The initial dose has 0.06 moles of medication dissolved in it. And 0.06 moles times 148 grams per mole is equal to 8.88 grams. To obtain our final answer, we subtract 8.88 grams from 21.312 grams and get 12.432 grams. This is how much powdered medication our nurse should add to provide a safe and effective dose to this patient. Before we close, there is one more topic that's important to go over in regards to diluting a solution. In a laboratory environment, there's a particular type of dilution that is very often used, and is called a serial dilution. A serial dilution involves diluting a solution multiple times in series, which is where the name comes from, until a desired concentration is achieved. To accomplish a serial dilution, we use a parameter called the dilution factor, which has the variable capital D with a lowercase f as its subscript. The dilution factor is equal to the total volume of the final resulting solution divided by the volume of the initial solution, which we call a stock solution because it's coming from the laboratory stock of chemicals. We then derive the formula C2 equals C1 divided by the dilution factor D sub f. In this instance, C2 is the final concentration, whether mass or molar, and C1 is the initial concentration, whether mass or molar. This is how a serial dilution is done. On the left, we have our stock solution, which has a molar concentration of 1m. If we transfer 1 milliliter of this solution to an empty test tube and then add 9 milliliters of pure water to said test tube, that's what we call a 1:10 ratio solution. It's 1 part initial solution to 9 parts pure solvent. That essentially divides the molarity by a factor of 10, so the molarity of the test tube liquid is now 0.1 m. Now, let's say we take 1 milliliter from this first test tube and add it to a new test tube with 9 milliliters of water, essentially repeating the process but with our diluted solution instead, therefore making our diluted solution our new stock solution. This second test tube now contains a solution that is 0.01 m in its concentration, a tenth of its previous value. We can repeat this process as many times as we like, dividing the molarity by 10 each time until we reach a concentration we like. In all such instances, the dilution factor is equal to 10. Remember, the dilution factor is the final total volume, which is always 10 milliliters in all the above test tubes, divided by the volume of the previous solution that was transferred, which was always 1 milliliter. 10 divided by 1 equals 10, and if we use our formula up here, we'll notice that all we're doing is dividing the molarity of the previous solution by 10. This gives us the molarity of the solution that is next in line, a value which is always 1/10 of the previous solution's concentration. In our next video, Unit 4, Video 3, we will introduce solubility. Thank you for watching.